In this video, we are going to focus on the complex plane. So when we talk about the complex plane, we're going to think about a real axis and an imaginary axis. So the real axis is going to line up with the x-axis, and the imaginary axis lines up with the y-axis. When I think about what a complex number looks like, we're going to think about it in terms of the real component and the imaginary component. So let's look at number 11. In number 11, we've got the point 1 plus I. So 1 would be the real component, and the number in front of I, which is also a 1 here, would be the imaginary component. So when I graph this, I'm going to move, starting from the origin, 1 along the x, and I'm going to move up 1 along the y, and there is my point 1 plus I. Let's look at number 19. In number 19, we want to graph 3 minus 4i. So I'm going to switch to a different color here. So we're going to move 3 along the x-axis and then negative 4 along the imaginary axis. So 3 and then down 4 is going to give me the point 3 minus 4i. Let's say we want to graph the point negative 2. So negative 2 is going to be negative 2 plus 0i. So we're going to move negative 2 along the x, and we're not moving up or down. So there's our point negative 2. And then let's do one more, maybe number 20. 2 plus square root of 3i means we're going to move 2 along the x. Square root of 3 is a little bit less than 2. So somewhere around here maybe. So 2 plus square root of 3i. So that's how we graph them. So let's examine complex numbers a little bit more closely. When we talk about a complex number that's in the form of x plus yi, so we've got this real component and the imaginary component, we could think about the magnitude or the modulus of z as the distance from the origin to that point if we think about it in terms of x and y. So let's think about our xy axis. Remember, this is the imaginary axis when we're talking about complex numbers. If I have a point, maybe it's 1 plus 2i. So 1 plus 2i would look like this. So I'm moving along the x1, now moving along this imaginary axis, which is kind of like my y-axis, 2 units. The distance from the origin to that point would be really that hypotenuse length here. So I'm thinking about this as x and this as y. So if I think about that Pythagorean theorem, which is what's tying everything together with that right triangle, x squared plus y squared is going to be equal to my distance here, which they're calling it z squared. So z would be equal to the square root of x squared plus y squared. And we call that distance the modulus or the magnitude. That's how long that is. And if we think about complex numbers, remember back when we talked about quadratics and we had complex numbers back in pre-cal algebra, we said they always came in pairs. And if we had a number, maybe 2 plus 3i, then its complex conjugate would be 2 minus 3i. So the difference is that they are different signs on the imaginary component. Well, it turns out that the modulus of z is equal to the square root of z times its magnitude. All right, so let's look at that for our example here, 2 plus 3i and 2 minus 3i. And I'm going to just scoot up so I have a little bit more room to write here. So think about where 2 plus 3i lives. 2 plus 3i is going to live at this point here. If I were to talk about the modulus of z, that would be the distance from the origin to that point. This distance is 2, this distance is 3, so the modulus is going to be the square root of 2 squared plus 3 squared, which is the square root of 4 plus 9, or the square root of 11. What that theorem is saying is that we could find the modulus by taking the square root of z times its complement. So let's do that. Let's take z times its complement. So we're going to have 2 plus 3i times 2 minus 3i. That's going to be equal to 4. Outside would be a minus 3i. Inside, minus 6i. Insides would be a positive 6i. And last would be a minus 9i squared. So you can see how the middle terms cancel. And we know I squared is the same thing as negative 1. So that gives us an 11 for z times its conjugate. So the theorem says that we could find that modulus by taking z, multiplying by its conjugate, and then taking the square root. So we're going to get square root of 11, which is the same thing we got when we used that theorem, square root of x squared plus y squared, to find that distance between that point and the origin. So you've got two ways to think about it. So it turns out that we could take any complex number and we can think about it in terms of a circle. And anytime we think about things in terms of a circle, we can think about things in terms of sine and cosine and a radius. So that distance here, that modulus from the origin to this point on the complex plane, we said that that was the modulus of z. Well, if we were to think about this in terms of a circle, then that's going to be equivalent to finding the radius of z. So that's where they're making this statement here. Now, because I can think about things in terms of circles, I can think about things in terms of sines and cosines as well. And as long as I know that angle from the positive x-axis up to this point, which we could find using the tangent, right? We call this guy theta. Then the tangent of theta is equal to y over x, which we know because we know a value for y and a value for x. If I know that theta value, then I can rewrite this point that is in a complex plane in polar. And we would do that by thinking about what that radius would be and multiplying it by cosine theta plus I sine theta. Because remember, x is equal to r cosine theta, y is equal to r sine theta, and if we were to factor that r out, we can rewrite it in terms of cosine and sine. And then we could actually take this a step further, and we can use Euler's formula. Euler's formula says cosine of theta plus I sine theta is equivalent to e to the I theta. So then if we just multiply this guy by r, then we can multiply this side by r also to take it from complex to polar and then to another form of polar using Euler's theorem. So a lot of fun stuff happening in this section. So let's play with some of these ideas. Let's look at a few examples. So let's look at 23. We're going to convert from complex to rectangular. So we're just going to do what it says to do. Find the cosine of 120, find the sine of 120. So we're going to have cosine of 120. We're going back to our unit circle here. So it's going to be negative 1/2. Sine of 120 is square root of 3 over 2. Remember, that's multiplied by I. And if we were to simplify that, we're going to get negative 1 plus square root of 3i. So we've taken this from sines and cosines to something without sines and cosines, all by simplifying. 26 is going to work the same way. So that radius is 2. Cosine of 5 pi over 6 is negative square root of 3 over 2. Sine of 5 pi over 6 is 1/2. And I'm just going to distribute that 2 through. So there's my point. So let's go the other way. Let's say we want to go from complex to polar form. That one takes a little bit more work. I like to start by drawing a picture of what's going on. I think it helps. So the first point is at 1 plus I, which is here. So this is 1 and this is 1. So we need to figure out what our R is, which is the modulus of Z. So it's going to be the square root of x squared plus y squared, which is going to be the square root of 2. And then we've got to figure out what theta is going to be. And to find theta, we're going to use tangent. Tangent of theta is equal to opposite over hypotenuse. Y over x, opposite over adjacent. And then where is the tangent equal to 1? That's at pi over 4. So then our point would be, I'll call it Z, or cosine of theta plus I sine theta, which is square root of 2 cosine of pi over 4 plus I sine of pi over 4. So if we want to write this in exponential form, we know R cosine of theta plus I sine of theta is equal to RE to the I theta. So then in exponential form, this is going to look like square root of 2 e to the pi over 4 times I. So polar form and exponential form. Let's do one more of these. Let's look at number 21. In 21, we were looking at 3 minus 4i. It's going to help to draw a picture. So 3 minus 4i. We've got to find that modulus. Z is equal to the square root of 3 squared plus negative 4 squared. So square root of 9 plus 16, which is 25. So our modulus is going to be 5. We've got to figure out what theta is going to be. So we're going to use tangent. Tangent of theta is equal to negative 4 over 3. If I take the inverse tangent, I'm going to get negative 0.93 radians. And I'm going to write this in terms of radians, all because they're telling us that they want that theta value between 0 and 2 pi. And since I'm thinking about negative here, and they want that between 0 and 2 pi, let's add 2 pi to it so that we can force theta to be a positive value between 0 and 2 pi. And I'm doing that in my calculator off to the side, and I'm going to get theta to be about 5.36. So my Z value is equal to R times cosine of theta plus I sine of theta. If I want to write this in exponential form, using my exponential form here, it's going to be equal to R e to the I theta. Theta is 5.36 radians, so there's my exponential form.